Yeah, good afternoon. Okay, I will be talking about some problem based on some recent research that I have with joint work with Joe Lope. The um, the motivation for this problem is in the realm of differential geometry. So I will be giving some preliminaries on the subject of the Sasaki structures. And then I will try to explain briefly how we describe the local moduli of some interesting metrics on links of isolated hypersurfaces. So let me start with some differential geometry background. We will be defining some geometric structure on a odd dimensional manifold, real dimensional manifold, in principle. And it combines several structures, or several tensors to be more precise. A vector field that usually is called a rep vector field, a contact form that gives you some sort of transverse symplectic geometry, and of course an almost complex structure that can be extended to something that is called an almost contact structure on the manifold. And of course also a Riemannian metric defined as you see in item 3. And also we would like the rep vector field to describe some geodesics. So we mainly say it in different fashions, saying that the rep vector field it's Killing vector field. And also we would like since this rep vector field is going to define a one-dimensional foliation, then the transverse space, the quotient space will define a very nice object that we will like to exploit. The contact one form, will define a contact bundle or a codimension one subbundle, the tangent bundle, and this contact bundle will determine a complex a CR structure actually on this contact bundle, and we will require this bundle to be integrable in the usual sense. Usually we call this an almost CR structure that is integrable. Sorry. So the interesting thing about having a Sasaki manifold is that it defines two objects in between. It's defined as between, or in the middle of two Kähler geometries. The first one is given by the metric cone. So you take the manifold M and you just take the product of the manifold by R plus, and then you define a metric that conifies this product manifold. And if the original manifold M is Sasaki manifold, then the cone metric defined here will be Kähler. Also, as I was telling you, the rep vector field, this that never vanishes, determines also a foliation, and the quotient space or the Hilbert space determines a Kähler structure too. So usually you say the transverse structure is Kähler. So when the rep vector field defines a regular foliation, then the quotient is a manifold, and one obtains this interesting diagram that tells you that you have a manifold with all these tensors that it's called Sasakian, but it's related by two Kähler geometries. One, the cone, give you some affine object, non-compact object that is Kähler, and as a transverse space give you a compact manifold, a Kähler contact manifold. For instance, we will be looking at problems where the manifold M is originally of dimension 7, then the cone will be of dimension 4, it will be Kähler, so we will a non-compact Kähler object, and the transfer space will be a six-dimensional manifold that also is going to be Kähler. And how can we produce examples on this scenario? We will try to actually do it in the scenario where the foliation is quasi-regular. That means that the quotient space will have some singularities, and those singularities are going to be of quotient type. So actually, the quotient space will be an orbifold. So in our scenario, we will have in general a cone that is going to be an affine variety. Our manifold that will be giving us a link that is the intersection of the affine variety, a set of zeros of some nice polynomial intersected with a sphere. And as the projective or as a transfer space, we have in that's the quotient of the affine cone by the C star action. That's the orbifold associated. We will a little bit more specific here. We will be working with a set of zeros of certain polynomials in general. We would like this polynomial to have some isolated singularity only at the origin. And then we will define the intersection as Milnor did in the 60s. Take the intersection of the preimage and with a sphere, a small enough sphere, and then you will have some transverse intersection, and then link will be a smooth manifold of dimension 2n-1. And topologically, it will be very simple because all the homotopy groups, or most of them are, well, let me say a different way, it's going to be n-2 connected. So we want to have some control on the topology of the link. So the link it has some simple topology in general. But we would like this polynomial to have a natural action, a C-star action. So we will be focusing on weighted homogeneous polynomials with certain degree and certain weights. As you see, the definition of a weighted homogeneous polynomial is given there. It's a generalization of how you construct the homogeneous polynomials. And then we will actually take these sort of functions or polynomials to describe some link. It's natural that the link is going to admit an S1 action, and that S1 action will define or determine this red vector field, and that will give you all the tensors that you need to say that the link admits as a second structure. Actually, it's going to be quasi-regular. So what you obtain in general is some sort of diagram like this. You have the affine variety, you remove the zero, and you consider this as included, of course, in Cn+1. That will give you a link, no? And the quotient space of the link by the S1 action induced by the natural C-star action on this weighted homogeneous polynomial give you the orbifold. So this is a generalization of the Hopf ration, actually. But that gives you some idea that we can try to track down the geometry or the particular features of the geometry of the Sasaki geometry of the Sasaki structures in terms of these algebraic objects, the affine variety and the orbifold associated to it. So we will focus on polynomials that are weighted, in particular these invertible polynomials. And of course, metrics that have some nice properties. The Einstein metrics are those metrics that have the following condition: that you take the Ricci tensor of the metric that is proportional to the metric, and that constant of proportion, that constant of it's usually determined by the scalar curvature of the manifold. And we will focus on those, and we will focus on links with certain nice topology, in this case with Q homology spheres. We will mainly, what I'm saying is that the link will have will be called rational homology sphere or Q homology sphere if the homology groups with rational coefficients are equal to the ones of the sphere, or the sphere of, in this case, of dimension 7. In previous works, we established that the existence of Sasaki-Einstein metrics on links of invertible polynomials. We focus on the following types. These types are the cycle types, the polynomials of this sort, this kind, with some arithmetic conditions. Notice that the degree and the weights satisfy interesting. They are co-primes, the elements of the weight of the action. Or we consider this Thom-Sebastian sum of certain polynomials that are cycle Fermat, cycle Brice-Confam, chain cycle, or cycle. Using the techniques developed 40 years ago, we could understand the topology of these sort of links, and combined with some results of classification of threefolds by Collar, we could establish the existence of Einstein metrics on links associated to all these types of polynomials. So it's actually all in dimension 7. That's it. All the types are given by this. Of course, with some arithmetic condition that it's called the Fano index, that these polynomials with this they can be considered as inside a weighted projective space and with certain degree. So the degree of the polynomial in that weighted projective space has to satisfy this condition. The Fano usually is called the Fano index. What is interesting about this sort of this kind of polynomials and is that, of course, they give you some rational homology spheres that admit Einstein metrics. So, in particular, the associated affine cone must be Calabi-Yau, and the quotient space, that is the orthogonal associated to the problem, is a rational homology complex projective space. So the information that we're going to, or we discovered, we found on these links can be interpreted in these two scenarios. So let me briefly, I'm not going to define exactly what the local model of Sasaki-Einstein is, because it's mainly a deformation of the space of orbifolds associated to it. We have the following two results that actually give us the main, how could I say that, these two theorems actually give us the key to how to compute the moduli of these links. So the first one is telling you that whenever you have a quasi-smooth weighted hypersurface, when I say quasi-smooth, that means that the affine or the weighted homogeneous polynomial considering on Cn plus 1 has only one singularity at the origin. And if you have some orbifold, as explained there, then you obtain a moduli just deforming the space of monomials associated to it. In a certain sense, that's what I'm going to show you briefly in a moment. So what you obtain is that actually the space of the formations of the orbifold can be computed at the dimensional level, of course, as the set of sections or global sections of this projective space, weighted projective space, in this fashion. In all our cases, the group of automorphisms of the orbifold will be zero. So we won't be worrying about it. So in particular, if one find these numbers, one will have the number of possible inequivalent Cuadros-Einstein metrics on the orbifold. All these, of course, are singular orbifolds because we are on orbifolds. But the next theorem, by the way, the first theorem was proven by Boyer, Galitsky, and Kolar in a paper in 2005. And the other theorem was also proved by Kolar, by Boyer and Galitsky in 2008, I believe. And the second theorem tells you that the manifold, actually, if you want to look at the possible space of deformations of the quasi-regular Sasaki-Einstein manifolds, then you just have to look at the space of deformations of the orbifolds. So the key will be to understand actually this piece. So for that matter, we have to basically count monomials of the possible deformation for the polynomials. So the key is to consider monomials of this type, of course, with the exponents being integers. So which is, we want these polynomials to be of degree, of certain degree, because we are trying to compute this with fixed D or with fixed WE. So we will have to solve this Diophantine equation. And of course, if one tries to do this with no restrictions, it's not possible. However, we found some arithmetic conditions that prescribe the topology of the link, and then therefore we could restrict our problem or solve our problem subject to some other conditions, natural conditions, to preserve the topology of the link. So the first problem is this one, the cycle type. And the conditions that are given here are very natural to this problem. And then we have some condition given by simply by the form of the polynomial. And then one can play a little bit and with this, and the fact that we are dealing with a rational homology sphere allows us to, through the Alexander polynomial for links, describe the weights of the action associated to the polynomial in terms of the exponents of the polynomial. And from there,
sorry, Dr. Jaime, sorry for interrupt you, but about your time, still have 3 minutes.
Okay, I will rush. Thank you.
Thanks.
And then with these conditions, we are able to find the solutions for this problem in the cyclid case. And actually, we are able to find explicitly the generators of this set. And also remember, we need to do it not only for D, but also for the WI, sorry. And for this, we also prove that the generators are singletons. So at the end, we are able to describe the set, the moduli actually explicitly of the orbifold associated to the cyclid polynomial with the conditions that I explained before, in terms of actually the span of these monomials by the group of automorphisms that can be given like this. For each, those come from, of course, these restrictions. And it's not surprise, at least for us, that the dimension of the moduli is 0. So there are no deformations, no trivial deformations for the orifice, and therefore there are no trivial deformations for the links. However, going very fast here, for the remaining cases, now again we find some arithmetic conditions, and we are able to split the problem of solving the Diophantine equation in terms of two Diophantine equations, in certain sense, isolated one from the other. And then after that, we compute the generators, and we compute also the space of global holomorphic sections that is actually the monomials, no? Associated with quotient by the group, and we obtain also the moduli space is given by something like this. One has to be careful with some computations here. And also for the type 2, for a type 1, for a type 2, and for a type 3, we are able to do it. And therefore, in particular, for the links, we are able to also describe the moduli then, no? Because if we are able to describe the moduli of the orifice associated, with those conditions, we are able to describe that at least at the dimensional level, the moduli of the rational homologous figures, in dimension 7 that admit Einstein metrics. And this is given by this expression in general for any of the cases, of the 3 cases for mass cycle or cycle type or cycle. So what I'm saying is that if you have one rational homologous figure that admits the Sasaki-Einstein metrics, it has to come from a link that is a cycle type or one of those Thom-Sebastianisms. And for all of those, for the first case, the moduli space is 0, or the dimension of the moduli space is 0, but for the other cases, the dimension of the moduli is given by this. I think I stop here.
Thank you so much for your great information, Dr. Jaime.